All right, so we're starting with SQL. So can anyone tell me about SQL? Anything you know?
Databases.
Databases, all right.
Query language.
Yep. Does it just do queries?
That's what they're
You can
called,
query.
but it does other stuff. Go ahead, Everett.
Oh, yeah, you can query, update, delete, append, all sorts of
Yeah.
things.
Yep.
It's
Okay.
pretty standardized across different platforms. So if you can query a Postgres SQL database, you can query a SQL or MS SQL database.
Yeah, so that's a good point. So there are SQL itself is, I'm not sure if there's like if there's like a body that, I'm sure there is a body that officially regulates standard SQL, but there are tons of different flavors. Basically every database system will have its own implementation, which will be slightly different, but it's like 99, maybe 99.9% the same everywhere. So you'll see as you're, as you maybe are doing these challenges or just learning about this in general, you'll see, there's like MySQL and Postgres, and there's 1,000 SQLite even, which we'll see later. There's 1,000 different flavors, but they're all basically the same. So I wouldn't get too hung up on, specifically, oh, I need to search for Postgres. How do I write a select statement in Postgres? You can, but it's usually not necessary. Okay, so we have, so SQL can do things like it can make queries, it can create databases, you can insert data, you can delete data. Okay, so what is all that stuff called, that collection of operations?
Is it CRUD?
Yeah, CRUD. So can you tell me what CRUD is?
Create, read, update, delete.
Yeah, it's kind of a standard acronym. So most any web application can be described as a CRUD app. So it does create, read, update, and delete or destroy, which basically just means it's a web application and it has a database and you can change the data in it. So when you create an account, you're creating something. If you, change your address, you're updating it. If you're, making a request and just looking at what your address is, that's a read. It's a read operation, and delete would be, deleting your account. So, and that's what we're going to be doing. So your projects will be CRUD apps, barring special circumstances, but you're going to have to learn to tie in basically database operations to your web app. It's difficult to make an interesting application that doesn't have a database attached to it. So that's why it's important to know about SQL and databases. And as the course progresses, so we're going to start with raw SQL, like real SQL queries. But as the course progresses, we're going to use some adapters. So we'll see that we'll use Python to interact with the database. So we'll have a layer of abstraction in between what you're doing in the actual SQL commands, but we start with raw SQL so that you understand what you're doing, so it doesn't just seem like magic to you. All right. So we're talking about databases. Is there just one kind of database?
There's flat.
Go ahead, Everett.
Oh, so there's flat file databases, relational databases.
Yeah. So there are different kinds. So the kinds of databases that we're going to be primarily concerned with are relational databases. But there are other kinds of. So there's SQL databases and there's NoSQL databases. Yeah, and there's one, but a relational database, one of the things it does is it basically enforces a schema on your data. So if I want to, for example, I have an account and I want to update my address or add a new address, there are, it's kind of like an instance of a class. There are certain fields that I need, and I can only have those fields. So if I try to create a new address with some other random field that it doesn't have, like, if it doesn't have a field for apartment number, I can't add an apartment number. Whereas a NoSQL database, you can think of it as like a giant object. Or, there are also like file system, but a standard NoSQL database, it's almost like a giant JSON object or something, where if I want to add something to the database, I don't have to follow a particular schema. So I can have a million addresses and they can all be formatted a little bit differently. So there are certain, there are times when you want one over the other, but we're going to be focusing on relational databases. That's kind of the foundation. All right, so let's take a look here. I'll share my screen. Okay, so I have this, pseudo database. So I think you can basically understand a database table as a spreadsheet. And we have columns, which are the, basically all the elements in a given row. So we have columns and we have rows. And there are different terms for these columns and rows. Rows are sometimes called records. The whole table can be called a relation. So there are different terms, just so you're aware of it as you're looking stuff up. Don't get too hung up on that. Okay, so we have this this database. So just looking at this database, what is this database for?
Customers.
E-commerce.
Yeah, this could be for like an e-commerce site or something. So what would the title of this database be?
It's not split out, but it would be two of them. It would be like a customer database and an order, or a customer table and an order table.
Okay, so you think that this is kind of doing two things?
It is, but I think it's really designed just to do orders, and they just have the names there.
Okay, yeah. So another way of thinking about tables is in terms of what's called grain, which basically means what is a row. So what is a row here?
Like a customer.
Okay, so it's a. So what if Sally makes
The rows are,
order?
it's a record. It's a record of an order. Each row is a single record of an order.
Yeah, so it's a little hard to describe for a couple reasons, but yeah, so I would say that as it is right now, this is in order. So I would say that every row is in order. It represents an order. It's an instance of an order. But there are some issues with this because, as you said, is it a customer? Is it an order? Is it a customer order? Yeah. So what are some issues with the way that this is designed? What are some potential problems or drawbacks?
You can mistype the address in for Sally, and there'll be two addresses.
Yeah. So now Sally Smith order. So maybe she has to type in her address every time, or however this works, but somehow this address gets corrupted. And having bad data or regular data is a constant issue if you've ever worked with databases. So this kind of stuff will definitely happen. So we have Sally Smith, and now she, I guess, has 2 addresses. So what happens? So one issue is that would be called something like data integrity, right? So we can't really trust this right now. What happens if Sally Smith moves?
She'll have multiple addresses in the database and you don't know which one is the correct address.
Yeah, so she could potentially move, and she moves to the big street now. So now we have an order, and she's moved to Big Street. So what is her address? So now we have to, now she either has multiple addresses, which we might not want, or we have to go back and change all of these other addresses. So we have to go back and update, every single record that we have and change her address there. Which again creates issues with, it's easy to not do. And if you have a huge database and most of it is automated, these things can happen without anyone really knowing about it. So it's like it's basically like a bug. So if you're expecting customers to have one address, and all of a sudden they have multiple addresses, or if you're trying to identify customers by a combination of name and address, then you might think you have more customers than you do, or all kinds of things can happen. So this is not good. The main problem here is that we have redundancy. So we have a name and an address, and really let's assume that this address is not changing. So we have, I'll change this back to small. So we're duplicating this information. And again, if you imagine this at scaling up, we have millions or billions of records that cost money to store. And so now we're, maybe not doubling, but we're increasing the storage that's necessary for a given record. We know that this is her address, but we have to duplicate that every single time. We have to duplicate her age every single time, her birthday every single time, even her name every single time. So we want to avoid doing that.
So there could be more than one Sally Smith too.
Yeah, absolutely. So that's another issue. So how do we, okay, so let me do this.
Have to assign a customer number maybe.
Yeah. So let's just say that the world is a big place. Let's just say we happen to have another Sally Smith who happens to have the same address and the same age and birthday, happens to order the same thing. So do we have two? Is this just a duplicate record, or do we actually have 2 different orders here? And how would you know? So
You wouldn't on this one.
yeah, so it would be difficult to tell just by looking at this. If you had, you could call up Sally Smith and ask her, or maybe she has a twin sister with the same name or whatever. But yeah, so this is a problem, and the problem is that we haven't defined a unique key that will uniquely identify every single record here. So another important thing that you should have for a database, a relational database, is you want to make sure that that each row is unique and can be uniquely identified. There's a couple ways to do that. One is you use a combination of values that already exist, right? So if I think, so let's ignore this edge case for right now. If I know or decide or whatever that name and address have to be unique, right? So you're not allowed to have, in our database here, you're not allowed to have an entity that has the same name and the same address, or the same name and address and birthday, or the same name and address and birthday and favorite color. So you can choose combinations of columns that you already have, and enforce uniqueness. So you wouldn't be able to create a new record. You wouldn't be able to create a new record. So in this case, yeah, we'll see once we actually split this up how that would work. But yeah, so you want to be able to have a unique key. So one way is to use a combination of columns. The other way is to just have what's called a synthetic key, which is almost always just an auto incrementing number. So your first record, you'd have another column here. This would be like ID. This would be 1, 2, 3. So we have this, this, not a dummy column, but we have this column that only exists to ensure that every record is uniquely identifiable. So we have this ID column, and it just auto increments. Every time we add a record or a row, this will increment by 1. So this is basically how we're gonna handle this. You definitely can use combinations of keys, but later on we'll see when we get into Django. It's just this is how we're gonna do it. So we'll use some capabilities that are built into PostgreSQL and basically every other database that will auto increment that for you. All right, so that's enough kind of general, I think general discussion about databases. Any questions so far?
Yeah, really quickly. So
Yeah.
in this case, I do remember the beginning of the lecture from last Thursday. In this case, we would want to separate out this. It's like 2 tables, right?
Yeah, for sure. Yeah, that's actually where I was gonna go next.
Thank you.
But yes, we would want to. So we talked about some disadvantages, just real quick for the sake of objectivity. There are certain advantages to doing it this way. Can anyone think of any possible advantages of having one table with everything in it?
Super simple to create.
Yeah, it's simple to create. What about queries?
You don't have to do any sorts of joins or anything like that. It's just everything's there.
Yeah. So it makes querying simpler. It makes creation of the database simpler. It could make queries faster because we're not doing a whole bunch of joins on different tables. So there are some advantages to doing it like this. But just the point is you have to think about, like everything else, when you're designing a program, there's usually 30 different ways to do it, and you kind of think about what the needs of your application are and what's the best way to do this, and in the future, are we going to be scaling up this way or that way, and how should we handle that? Just keep that in mind. All right, so let's so we're gonna focus mostly on talking about designing a database. So when you're designing a database, you're typically gonna you're gonna be doing it from the perspective of a web application. And when you do that, the first step is to think about what kind of entities your application requires. And this is very similar to when you're designing a program that uses classes. So you design a program that uses classes, you have to think about, okay, what is my problem? how can I break it up into chunks? And that first layer of breaking things down is probably going to be classes. You'll have different classes that are kind of in charge of basic functionality, and then you determine how those classes will relate to each other. But the first step is to create those individual entities. So let's do that. Let's do that here. So we have this table. And what entities should we pull out from this? Do this way.
You can pull out like the personal data or keep the personal data and move out all the order information.
Okay, so we don't, let's say, yeah, let's say for now, we don't want to like lose any information, but we just want to create, we want to pull out from this kind of mess individual entities. So we want to create smaller tables that are more focused and specific.
Customers.
Okay, we could have a customer table. What other entities might we have?
Orders.
Okay.
Items.
Items, okay. Yeah, we could have items.
Addresses.
Yeah, address. You can basically make these singular or plural as you like. But yeah, so I think that's probably good for now. We could definitely keep going. We could make things more complicated, but something like this is good. So we have customer, order, item, address. So what fields or columns would a customer have?
Their customer ID to make it unique.
Okay. So everything basically will have an ID. Yep.
And first name, last name.
Okay.
And then a link over to their address.
Okay. So let's not. Yeah. So that's a good point. Let's just focus on the entities themselves, and we'll talk about how they're connected afterwards. So we have customers. We'll keep it simple. Let's say this is good. What about an order?
You also had age in there too.
Okay. Okay, so I'm gonna simplify this, and let's just say we have customer and address. So what fields or columns do we want in our address?
Street.
Okay.
City. State.
And again, we could get more complicated, but I think this is good. So we have our entities. So we have this big mess, and we're going to simplify and pretend that we only care about these. So we pulled out the entities that we want, and then once we had those entities, we can go in and add all those fields. And sometimes as you're adding the fields, you realize that maybe I should pull this out. So is there any way? Well, so let me just say, we could potentially pull out first and last. So there's basically no end to how you can do this. We could have a name table, and we could have like first, last, last, title, suffix, right? So we could have if depending on the needs of the application, maybe first and last is not quite enough. So we want to pull this out into its own entity. So that's something that, as you're doing this, it's not just a single, do this, then that, like create the entities, then create all the fields. Sometimes you need to circle back and pull out a new entity as you're doing this. Okay, but we're not going to make it that complicated. All right, so we have our entities now. Let's say customer and address. Now we need to talk about how they're connected. So we have thought about our application, our imaginary web application. We pull out all the entities that we need. We figure out all the fields that each entity will have. Now we have to connect them together. Because if we just leave it like this, we don't have to worry about connecting anything because it's all there, right? But if we pull all this stuff out into individual tables to reduce duplication, right? So this is going to save us some memory because we just have to store this address one time instead of every time Sally Smith makes an order. But if we want to find out what Sally's address is, well, how are we going to do that? So we can find Sally and we can find and address, but how do we find Sally's address? So that's the problem that we're going to solve now. All right, so there's actually a link to this in one of the challenges for today. When it comes to databases, I would say, classes in general, it's good to draw things out, to give yourself some kind of visual representation, whether that's, pen and paper is fine, whiteboard's fine, or, some, draw IO or something like this. But it's a good idea to actually draw it out so you can, it forces you to be clear about it and you can reference it as you're programming. So it just makes things easier, I think. Okay. So first thing, we can just copy out our identity or our entities. So we have a customer and an address. Okay, so we have our two entities here, and let's just go ahead and fill this stuff out. I'm just going to keep it simple. So we'll do first, we'll do an ID. So there's, don't get too hung up on this particular application. There's a little, little mini kind of domain specific language for this, but I wouldn't worry about it. So PK means primary key, and that's what this is. So this in our database, it'll be an auto incrementing unique identifier, and it'll be the primary key. So the primary key is what uniquely identifies a given row. So the ID will be our primary key, and yeah. And then we have, let's say, first name, and yeah, well, okay. So we have all these entities. So the database, using a database provides a few advantages. And one of them is enforcing certain kinds of data integrity or data types. So if you write, if you write a function in Python or JavaScript, and your function requires, let's say, an array, and you give it a string, then it's not going to work. I mean, depending on what you're doing. And so databases have similar kind of type constraints. So you can tell your column, okay, my name column, I want it to be strings. So if you try to insert a number or a date or a float or whatever, it's not going to work. So you can do the same thing with your column. So we're going to say, so varchar is one such. There are like, I forget how many there are, maybe like a dozen or so different data types in Python. So varchar is, basically a string that can be with a max length, and the max length is 255, but you can, I think it's 255, but you can you can determine that. So let's say we do some research or whatever, we just decide that first names should be no longer than 100 characters. So we can set that. And if I try to insert a record, insert a new row into the database with a first name that has 150 characters, it will be rejected. Okay, so first name, last name. Do the same thing here. And then what else do we have? Yeah, we'll keep it simple. Actually, age, we'll do age. So age can be an int. And then, yeah, I think that's good for now. And then address, we'll do street, city, state. We'll have ID first. That'll be the primary key. Street can be our car. Just assigning arbitrary values here. City. And state, let's say states are abbreviations. You do, let's say, yeah, states have to have a two-letter abbreviation. All right, so we have our entities now, so we can look at them. So this is basically back where we were here, but now we want to connect them. So we have our entities, now we have to figure out how they're connected. And so the question you basically need to ask is, first off, the relationships can go both ways. So there's a relationship between customer and address, and there's also a relationship between address and customer. So just maybe those of you who don't have experience with databases, how would you describe the relationship between a customer and address? I know I limited my volunteer pool by, let's see.
So like a customer has an address?
Yes, yeah. Okay, good. So a customer has an address. Does a customer have one address or 10 addresses or 0 addresses?
Typically one.
Yeah, so it could be any of those. It could potentially, a customer could potentially have no address. A customer could potentially just have one address. A customer could potentially have, one or more, or you could even have a specific amount. So this is a question that, you'd have to figure out depending on the needs of your application. So if a customer had no addresses, that would mean that your application doesn't really care about addresses. So you don't need someone's address to do what you're doing. So for an e-commerce site, that probably wouldn't work. Depending on what you're doing, you probably need someone's address for credit card processing, for shipping, and so on. You could potentially, maybe for like an NFT or something. I don't know. I'm not really into that, but potentially you wouldn't need an address for that. But so yeah, again, it just depends on. It's not like there's not like an absolute answer here. It depends on what you're doing. A customer could have one address, so you could say, customer, you can only have one address, and that's saved. You could also have lots of addresses. So maybe you're saving them, like in your Amazon account or whatever. You have previous addresses that you lived at, and so a customer could have lots of addresses, and when you check out, you choose which one you want to use. So any of those could work. Let's just say, to keep things simple, let's say that customer has one address. So for our application, a customer just has one address. What about the reverse relationship? What about address to customer?
So
That-
you could have more more than one person in a certain address. So an address could have more than one person.
Right, yes. So, yeah, so an address, so you could imagine, let's say, like husband and wife or something living, they're both customers, so they both have their own, entry in the customer table, but they happen to live at the same address, so they'd have the same address. So each customer, the husband would have, the husband would have one address, so that follows our rules. The wife would have one address, that follows our rules. But the reverse relationship is different. So a customer can only have one address, but an address could be associated with more than one customer. And again, we could design it differently. We could enforce, we could say, a customer can only live at one address and that's it. That probably wouldn't make a lot of sense, but I'm sure there's a use case. But the point is, so if we think about the needs of our application and we decide, okay, a customer has to have one address and they can only have one address, but an address can be associated with more than one customer, then we say that that's a one to many. So depending on what side we're talking about, one address could have many customers, one customer, or many customers can have one address. So to express that relationship, you say that we're basically going to add a new row here. So instead of saying customer Bob lives at whatever, just like everything explicitly written out in one table, we're gonna create a key. We'll call it an address ID. And that'll be what's called a foreign key. So we have primary keys, which is a way to uniquely identify every single row in our table. And then we have foreign keys, which are ways of connecting to another table. So this foreign key is going to go from customer to address. And you don't need to worry about this notation here, but so what we're saying here is that, so notice these little, so we did a little bit of UML diagrams. You don't need to become an expert or anything, but this can just be useful to look at. So what this is saying is this single line means basically one, and this little crow's feet or 3 crow's feet, that means many. So if we look at this, we can say that a customer has one address. Going from customer to address, we just have this one, and going from address to customer is many. So a customer can have one address, an address can have many customers. And if we wanted, let's say, if we just wanted to query, well, we'll talk about queries in a sec, but if we just wanted to get, the customer's name and age, then that's an easy query. We just query this customer table. But if we want to get, a customer's address, then we have to query this table. And then we have to also join this table to that table. So we start with customer, and then this gives us a path to address. So we can say customer, give me this customer, and then look for the address. And then we can pull the address information and the customer. So when we query, we kind of rejoin. In some sense, we'll like recreate this table when we query. But this will be one table, this will be another table, this will be another table. Your application will be divided up into tables, and when you make queries, you can kind of join them together so you can reconstitute some imaginary master table like this. All right. Yeah, why don't we let's take a 5-minute break, and then we'll come back and we'll do some actual SQL. All right. So now we're going to actually implement. So we've gone through this design phase. We've thought about our application and the entities that it's going to need and how those entities are connected. And now we're going to actually implement this in SQL. So I have a screenshot of what we did. This is just for, for reference. So the first thing we have to do is create a database. And since we have Postgres installed, I'll do PSQL and then create the database. So I'm just going to call it e-commerce. Okay, great. So how do I create a database?
Create DB.
Yep. Okay, so did that work?
Yes, but how do we know? Is that the follow-up?
It will be, yes. So we know it worked because we didn't get an error. So that's good. Good bash style. Only tells you when you do something wrong. So how do we? Yeah. How can we actually verify that?
Type in PSQL.
Okay. Okay. So we're now inside of our database. And if I want to see so a database, is a big container and it can have lots and lots of tables in it. So let's see what we've got in it so far. We can do that with describe/d. Did not find any relations. So what's a relation?
A table.
Yeah. So again, this is a case where this is especially the case with databases, but there's about three or four terms for every single thing. So it's kind of annoying, but a relation is just a table. Okay, so I'm going to exit /q. Okay, so I'm back in my terminal here. So the first thing I'm going to have to do is we're going to create the database. We created the database, we're going to create the tables. Then we're going to insert some records, some rows, and then we'll make some queries. So we could do all of this on a command line. We can go in here and then we can write all of our queries here. But it's not really user friendly. I don't get highlighting, and if I make a mistake, it's just annoying. I have to retype everything. So rather than doing it directly there, I'm going to basically write a script. So we'll do it in a file and then we'll execute the file as a script. The first thing will be I'm going to write a SQL file. Why is that not showing up as a SQL file? Huh. That's strange. Is anyone else not getting highlighting when they do this? Let me just. I don't know. So we'll go ahead and do this anyway. I may not get the highlighting. So to create a table, we have two tables that we want. Split right. You have this customer and the address. So you create a table with the create table. And conventionally, the built-in SQL stuff, the keywords are capitalized, but you don't have to. It's not actually case sensitive. It's just a convention. So create table, and then we want to create a customer table. And our customer table is going to have these different fields. So it's going to have an ID. And the ID is going to be the primary key. And then we're going to have a first name. And that is going to be a var car. And we'll just say 100. And then last name, var car of 100. And then age. Is it integer? You have to specify, we'll see. Okay, and then we have an address ID. So we'll deal with that in just a second. So the other table that we need, create table address. And that's also going to be an ID, primary key. And street, which will be, just make it different just because, and then city. And then state. And we're going to add semicolons at the end of all these statements. So there's a couple ways to create foreign keys. So one way is to create the tables, and then you can actually have an alter statement, which will add everything afterwards. You can also create it just kind of inline all at once. So that's what I'll do. So address ID, and that's going to be an integer. Integer, we'll find out. And then we'll have a foreign key relationship. So we can look up key. We go through foreign key and then references whatever. We can try doing that. So foreign key. ID references. And then we do addresses. Address dot or address parentheses ID. Yeah. All right, so let's try executing this and we'll see if we get any errors. So we're going to execute this as a script inside, basically, or put it inside of our database. So I'm going to do PSQL and then the database. And I'll add this -f flag for a file, and I'll pass it tables.sql, and it will execute here. And then we have an error. So I think I have to add something else besides just primary key. So I think I have to add the serial command. So serial primary key. right, let's try this again. Okay, so now I have a syntax error here. So foreign key address ID references address ID. So that is wrong.
Address needs to be in parentheses. Like address ID. The first one.
Oh, okay. Just address ID. Okay, so one thing you'll notice is that the errors, the error feedback you get from SQL is not the best. So this error where this needed to be in parentheses, it just tells me there's an error at or near address ID, which is actually not too bad. It gives me the line number and it points here. So I know something's wrong here, but doesn't really tell you, doesn't tell you much. And then here, it's saying that relation address. So I've run this file a few different times. So what's the problem here?
It already exists, so it's going to throw an error. And
Yeah,
you
so-
could put create table like if exists. That way, if it's already there, it's not going to try to do it again.
Okay, yeah. So let's take a look at what's in our database right now. So we'll describe all of the, so we have an address table and a customer table. So let's go into, we'll describe the address. And we can see that here are our columns, ID, street, city, and state. And the types, so integer, varying, and then a character. And we have this ID, so we didn't have to specify this, but this is basically, it's basically gonna run this function every time we create a new entry, this next val function. So you don't have to worry about that. And then it's telling me information about the foreign key. We can describe the customer table and we can see the same thing. So the address ID, foreign key constraints. All right, so let's quit. And right, so as Everett said, we can add a clause basically. So we can optionally delete the table. So as we run the script, we can't like recreate a table that already exists. So we can basically delete it if it does exist. So we'll do that. Let's see. Drop. So I'm just gonna, oh yeah, I'll do it uppercase. Drop table if it exists. Customer, and we'll do the same thing here. Let's try running this again. So we're gonna execute this file, tables.sql, in our e-commerce database. Okay. So it drops the tables, and then I get an error here. It's telling me that relation. So what is relation again?
Talking about if a table exists.
Yeah. So it's dropped. So these two lines have executed. So drop table, and then at line 12. So SQL often tells you like the end of something. So that tells you that there's a problem somewhere above line 12. Relation address does not exist. So
You were referencing that table before you created the address table.
yeah. So this is one issue with adding the foreign keys directly on the table, is that you have to make sure that the order. So we have to create this table address first, because customer is dependent on address, basically. You can try executing this again. And now this works. We get this kind of notice, which is not an error. And then it drops both tables and then it creates both tables. So we should be good now. If we can go in PSQL e-commerce. We can describe all of the tables we have. And by the way, this table is, I believe it's just internal PostgreSQL. It's because we have the serial primary key here. You don't need to worry about that. Here are the tables that we created: address and customer. So we can see that customer looks right. All right, so we'll quit this. So now that we have our database, we need to insert records. Must be missing a plugin or something. I don't know why I'm not getting it's not recognizing SQL file. That's fine. So, okay, so to insert to create, use the create statement, and to insert, use the insert statement. So insert into, and then the table. So we'll create some addresses first because customer is dependent on address. So we'll create some addresses first. So insert into address. And then here we need to list out the fields, except for ID, because that's going to get created automatically for us. So we need street, city, and state. So street, city, state. So we're going to insert into address, and we're going to supply these 3 columns and the values for those columns. Oops. The values will be, here's where we actually insert what we want. So 1, 2, 3 main. And the city will be, I don't know, Chicago. And the state will be Illinois. So that's our insert. I think we can get rid of this now. Okay, so we're going to write another insert statement. We'll just insert another address. So and Chicago, Michigan. I think there is Chicago, Michigan. All right, so we're just going to insert a couple addresses. Now we're going to insert a couple customers. So customers going to have first name, last name, age, and address ID. So insert into okay, I already forgot. First name, last name, age. First name, last name, age, address ID. And then you can actually break this up into multiple lines. The only thing that matters is this semicolon at the end. So values will be Bob. So another thing to watch out for is double quotes and single quotes. That makes a difference here. Age and address ID. So address ID is going to come from the auto incrementing ID. So we don't actually, you can't see this here, but let's say if he lives here, this will be the first one. So this will be 1. And I'll copy this. I'll do another one. choose it too. Okay, so now I have these statement, I have my tables created and I can try to insert this. So let's PSQL -F. Okay, and by the way, just so you know, the names of these scripts don't matter. Okay, so I've inserted 4 records, which looks good. So I can go ahead, let's go ahead inside our table, PSQL commerce database. We can check out our tables. So the tables look good, but how do I know if I actually was able to insert this information?
Do you have to query it?
Yeah, that's basically, so we've created the database, then we created the tables, and then we inserted information into the tables. And if we want to see what that information is, then we have to query it. So how could we query, let's say, the address table?
Type the name of
So-
the table, I think.
Okay, so yes, we are going to need the name of the table.
Select star from
Okay,
table.
so what is
Is the
the
capitals? Is select supposed to be capitalized?
Yeah, it actually doesn't matter, but yes.
Oh, okay.
Yeah, it's not actually case sensitive. It's a convention, and I'm lazy. But select
Star from, and then what table are we looking at? Customer.
yeah, we can do it. Let's do customer. And if I do this, so what happened there?
You don't have a semicolon on the end?
Yeah, it's kind of annoying, but you have to. So JavaScript, you can either have or not have semicolons in most cases. Here you have to have them. So if you just press enter and you don't have a semicolon, it's going to think that you just are running a multi-line query,
Oh.
which you can do, kind of like this. Okay, so select star from customer. We can see that we have this. So let's go ahead and we'll run a sanity check on our address as well. So select star from address. Got the semicolon again. And there we go. So it looks like everything is good so far. So let's now, so as we've just seen, we can do stuff like queries or inserts or whatever, just on the, in the interactive terminal here, but I think it's easier to do it as a script. So let's do that. So I'm gonna quit. We're gonna write another file here, which will be queries.sql. It's misspelled, but whatever. Okay, so queries. Well, so we've just seen, let's go ahead and rewrite these queries. So select star from and we'll also do select star from. All right, so I'm going to execute this script in the same way we've done before. So PSQL, the database -F, and then and we get both of these. So just as a note, this output is basically just, it's not necessarily usable. It's just printed to the console. So when we actually, soon we'll basically use Python, a Python library to interact with the database, and that Python library will take care of actually giving us back data that we can use in Python rather than just printing to the console as it is now. Okay, so we have these two queries. Let's say I now want to get everything that's in the customer table, but I only care about first name and age.
Instead of the star, just say first name and age.
Okay. First name, age, from. Save that and execute it. Yeah, and as you can see, comments are 2 dashes. So that's how you do comments. Okay, so this works. I see Bob and Sally, first name and age. What if I, so this is just, you know, string output to the console. So this column name is not really helpful. So I need to run queries, and I need to give the results of these queries to my boss who does some business analytics or whatever. And age is not specific. So is this like age in years or days or what? So I want to be specific, and I want this column to say age in years. Is there any way I can do that?
Yeah, I think there's something to do with like as, I don't remember the syntax,
Yeah,
but
yeah.
age as something.
Yeah, exactly. So we can alias these columns. So if we just say, you know, give me first name and age, by default, it'll print out here, but we can actually rename those. So as, age, in years. And we get the output. Again, we're not changing our actual data. We're not changing this table or anything like that. This is just for display purposes. But yeah, if this is easier or more meaningful, then you might want to, you can do that. Okay. So far we're just querying from individual tables, but let's say I want to see everything. I want to see everything in customer and addresses all together. So we have these two. So if we look back at our original thing, we'll ignore the order information, but we have just one big table that has everything we need in it. So if we wanted to get, you know, everyone, we'll do another query. So like everyone who lives in Michigan. How would we write that query? So I want to get the first names of everyone who lives in. Actually, that's not going to work right now. We have to do a join. So in order to avoid doing a join, yeah. So okay. So I want to get the first names of everyone who's over 70.
Use where? So
Yeah.
select first name from customer where age is greater than 70.
Okay. And that works. So we're just getting the first name column, and we're restricting using the where clause. So if we had a giant database and we wanted to get, you know, the first names of everyone who lives where state equals MI. Well, again, if we had our giant database, this would be easy. We just write this query, and we get the first names of people in Michigan. But we can't do this because we've pulled our data apart into 2 different tables. We can no longer do this. So how can we? So our state information is in one table, and our first name information is in another table.
Join.
Yeah, we're gonna have to join these tables. So can anyone help me out? Or maybe can anyone tell me kind of what a join is actually doing?
It references the, so the customer table has an ID to the address table, so it references that address table. And then instead of just showing a digit, it'll pull in the information from the other table.
Okay, so we need, we have these two tables. And we want to get something that's just one big long row that has information from both tables in it. But the question is, how do you line these up? So we want, all of these columns from customer. If we go back to this right here. So we basically want something that, let me copy this. We want something that kind of looks like this. It's got everything. But we have to line these up. So we have to match records from the address table or from the customer table to records in the address table. Do we have a way to connect those?
The primary key and the foreign key from the second table.
Yeah. So we have the customer table has this link to the address table. So we can line them up by the customer's address ID equals the address's ID. This is a little confusing because we're saying ID a lot, but this is the customer address ID is 1. And here we have the address ID is 1. So we can take this record and line it up here because these two match. So here's where we're going to join, and we can do the same thing here where we're going to join these where the customer's address ID is the same as the address's ID. So here's where we're kind of locking these together. So let's go back to our queries. So how do we actually do that? Well, we're gonna have to get both tables. So select star from, and the table that you start with. So there are different kinds of joins. I'll say that there are different kinds of joins, but we're basically just going to be concerned with the default, which is what you use most of the time, which is called an inner join. So an inner join will connect two tables together. You can also have multiple tables, but two tables together where some column equals some other column. You can do other things, but that's the basic 90% of what you're doing. So we're going to select everything from customers. We'll select everything from customers, then we're going to join. I'm going to write this on multiple lines. Join address. We're going to join it on. And how are we going to join it? We want customers. Yeah, go ahead. Yeah.
Oh, I was going to say, yeah, the customer's ID equals the address ID.
So it's the customer's address ID.
Customer's address underscore ID.
Yeah. Let's see, customers. I think it's just singular, right? So customer dot address ID equals address ID. So just the regular ID from address, which we have here. If the address's ID is equal to the customer's address ID. Okay, so
Then semicolon.
let's try running this. Okay, so now we get this giant, again, we haven't actually changed our data. We haven't changed anything in the database. This is just a presentation layer. But we've joined these tables together. So ID is 1. So here's all of our customer information right here. And then here's our, sorry. So this is all the customer information, including the foreign key address ID. And then here's the address information. And you can see that it's joined here. Address ID is ID, address ID is ID. So that's how you join these tables together. What if I just want, again, let's go back to this query. So I want the first name from, I basically just want the first name where the state is Michigan. How can I do that?
Where address.state equals Michigan.
Yeah, we can try doing that. Let's see where. State.
And then change the select from star to first name.
Okay. So what happens if I run it like this, as it is?
It'll give you that whole big long line, but
Yeah.
Sally's gonna come back.
Okay, so we just get Sally, but we get everything. So we don't want everything, we just want first name. So this is kind of maybe the downside of using a relational database and normalizing. So this process of splitting up all of our data from this big table into lots of smaller tables is called normalization. So there's some downsides to normalization. It makes the queries complex. If we just had one table, this would be a simpler query. Now we have to join. And if we had lots and lots of tables, we might have to join lots and lots of tables together just to get this single value. Let's see. Yeah, are there any questions? So this is the basic idea is when you're designing a database, you think of your application, in this case, like a web application, and then you think about the data that you're going to need stored, and you try to chop that up into entities, and then you figure out what fields or values or rows your entities are going to need, and then you can actually write the SQL to create the tables, address and customer. You figure out how they're related, and you express that with foreign keys. And then you can insert data and then query it.
So an inner join, that's default. And if you wanted to do the other, do you have to specify?
Yeah, so we could also specify inner join, but it's inner by default, so we'll get the same result here. There's also left join and right join and so on, but we're not gonna go into all that stuff.
Good.
So on these, should we always try and break it down as far as we can, or is it really just up to the designer?
Yeah, I mean, you can really go nuts.
Is there gonna be like a point of diminishing results on like performance, or is it really?
Yeah, so it's in general, there's a trade-off between storage and query speed. So the more you break down your tables into individual values, the less storage you're going to need, but the more complex your queries are going to become. So If you go back here. So we saw that even name could be divided up into lots of different table, or it could be taken out as its own entity, and you could have first name, last name, suffix, title, whatever. Address could be divided up. Even street could be divided up into like number, and then I don't know, name, and then type, street or lane or whatever. So you could pull street out of address as its own entity. So you can, I would say you probably don't want to go that far, but it depends on your application. So if you do that and you really make everything totally atomic and isolated, then yeah, you're reducing duplication, but you're gonna, especially if you have billions of rows of data and you're doing complex queries, then those queries are gonna slow down, which may be a problem. Like at a certain scale, that may be an issue. So oftentimes there's kind of an ideal of normalizing, like really going nuts and just totally normalizing and isolating everything. But in the real world, oftentimes there's this denormalization that happens. If you find that you're running lots and lots of queries that kind of are joining several tables together, you might just create a table that has all that information in it. So when you query it, you're reducing your speed, or reducing the time it takes.
Okay, so you're just basically finding the sweet spot depending on what you're making.
Yeah, it's a trade-off. So I wouldn't like go nuts. You can definitely play around and maybe as an exercise see how far you can break things down, and then try writing some queries. So even something as simple as this, where we just have two tables, you could definitely break this address down into one or two more entities, and customer, you could break that down also into one or two more entities, and try doing that, and then try running some queries, and you'll see you're joining like 4 tables together to get something like this. And if you have billions of records, then that, I mean, it really does make a difference. I mean, it's the difference between 30 seconds for a query and like 3 hours. So that makes a difference from like a day-to-day work perspective. If every query you're running is taking an hour, you're wasting a lot of time.
I could see where it would make sense to maybe pull the state out into a table, but then I would hate to have to do a join statement every time I wanted to find a state.
Yeah. So, but there's a trade-off there, because there's only 50 or so states. I mean, depending on what you wanted to include here, but there's a finite set of states. So your state table would be finite. Whereas if you do it here, if you have 1 million addresses, then you're duplicating the state information a lot. So there's a trade-off between, here, if you do it like this, you get faster queries. If you split it up, then you're using less space. Yeah, this is just a general, like, I wouldn't get too hung up on that. That's just, in general, how you think about that stuff. All right. Are there any more questions?